Good evening, all. Hope, okay, let us start the session. Okay, next, see, almost counter is over, right? And there is one more small part that I left in our last class. I told you we will be able to design any type of counter with the help of synchronous counter, right? That is any type of counter in the sense some general counting also could be possible in case of synchronous counter, right? Okay, let us see. Actually, we are discussing about asynchronous counter and synchronous counter, right? Now, while discussing about asynchronous counter, we saw up counter, down counter, right? Yes, they are simply called what? Up counter, down counter in the sense, I hope you all remember, in up counter and down counter, either we can go from 0 to 1, 0 to 7, 0 to 8, like 0 to 10, like 0 to 14, 0 to 32. Okay, whichever the counts that you want, you can just proceed and you can design its corresponding circuit, and we know how to design the circuits when we are having asynchronous counters. Now, in synchronous counter, what we saw, in synchronous counter, actually, what is the difference? In asynchronous counter, the one only thing is either you can count in up direction or you can count in downward direction, right? But random sequence, that is the random generation or random counting, is not at all being possible. Random counting means what? Suppose if you want to design, like if you want to count 0, that is odd sequence, like 1, 3, 5, 7, 9, 11, 13, 15, 17, like that. If you want to count only odd numbers, that is not possible in case of asynchronous counter. Like if you want to counter only even numbers, like the general conclusion is random sequence cannot be designed, because what we saw when I was discussing about what I can asynchronous counter, just right, the way that we are designing the counter is what? Simply helping us to count the values either in upward direction or in downward direction. Whereas when we are discussing about the synchronous counter, we saw ring counter is there, right? That is self started ring counter will be there, not self-starting ring counter will be there, Johnson counter will be there, right? Those things at all, we just went up with some four states. That four states might be anything, right? So in the same way, right, with the help of the flip-flop, right, in case of synchronous counter, any type of random sequence could be possible. That is the finalized conclusion. That is the one of the most advantage of your, that is the most beautiful advantage of our synchronous circuits, right? So let us design the general, that is, let us see the general procedures in order to design any type of circuits, right? Any type of counters, right? So the general procedures are the thing is, in order to design any type of counters, right? Step number one, right? See, some random sequence will be given to you, right? Some random sequence, that is, select the random sequence that will be given to you, right? Take the random sequence, right? Sequence will be given to you, right? You can just I'm giving random sequence in the sense, either it might be in proper order or it may not be in proper order, it does not matter. Just select any sequence that you want, right? After selecting the random sequence, you are requested to write the present table under, that is present state under next state. That is you are simply supposed to write present state under next state of the device, right? Present state under next state, right? You are supposed to write present state under next state immediately. Now, after writing present state under next state, you will have to write, that is, you are supposed to do required, that is, you are supposed to write excitation table, right? You are supposed to write excitation table. You are supposed to do, right? Design excitation table for the required flip-flop, right? For the flip-flop that you are going to use, right? So the using flip-flop for implementing flip-flop, right, which flip-flop we are going to use in order to implement, we will see, right? That is implementing flip-flop in the sense, it might be T flip-flop, D, T, whichever, that is JK, SR, whichever the flip-flop that you want, you can just take, right? After writing the excitation table, you are supposed to find out the characteristic equation or the relations between output and inputs, right, by putting them into the K-map. That's all. Final step is implementation, circuit implementation, right, with the help of K-map, right? So circuit implementation, right, with the help of K-map, right, with the help of K-map, right? Let us see how to design this one. With the help of K-map, we are going to design the final circuit, right? Fine. Shall we start our journey, right? Let us see how to design any flip-flop, that is any countings, right? So this is the general procedure, right? Let me take some random sequence, right? So let us do these things now, right? Now the thing is, for an example, given it is, right? So let us consider a random sequence is given it is 0 0, right? And then they said next they are going to 0 1, next they are going to 1 1, and then they are going to 1 0, and then they are getting back 0 0, and then again 0 1, again 1 1. It is continuous. Clear? If you observe this sequence, see there, it's decimal equivalent. First we have 0, and then we are counting 1, and then we are counting 3, and then we are counting 2, again we are counting 0. Is it proper order? No, right? See there, if you observe 0 1 2 1 2 3 is our proper order, but here we are counting some random sequence. First I am counting 0, and then I am counting 1, and then I am counting 3, not counting 2, and then we are counting 2, right? So that is the given general what I can say sequence, right? And you are requested to design the counter by using T flip-flop, right? So you are requested to design the counter for this given random sequence by using T flip-flop. That is the given question, right? That is the given question. Very simple, right? So step number 1, random sequence is given now, right? So with this help of this one, now first step, right? You are requested to write down the present state of the circuit, right? First step, write down the present state of the circuit, right? We will find all those things. Guys, listen here. Present state in the sense, first of all, how many states we are going to have in the present, right? In order to know the present states, right, first of all, we need to know the number of flip-flops that it should be required, right? In order to know the number of flip-flops, you can use the general formula that we saw already, right? 2 power n, which is greater than or equal to what? N. Whereas this small n denotes the number of flip-flops. It denotes number of flip-flop, right? Whereas we all know there is number of states, right? Now if you observe these things carefully, 1 2 3 4, this is the maximum number of states, and then again it is being repeated, right? It means in order to obtain, right, when these two guys are going to be equal, total number of states are 4. How it is possible? When we have 2 flip-flop, right? So the conclusion is, if I put n equal to 2, automatically which will be equal to 4. So the conclusion is, I am in need of 2 flip-flop in order to bring these 4 states. Clear? I hope things are clear now. Let's continue with this. Now in the sense, in this present state, so we are going to consider what? 2 flip-flop, right? So the first thing is, let us consider 2 flip-flop separately. This is the final step, right? So you are supposed to consider only 2 flip-flop. First let me draw the flip-flop here, right? Of course 2 flip-flops are there, and here we are going to, this is, let me consider this one as T0, and let us consider this one as flip-flop T1, and here we are considering Q0. Let me consider this one is Q1, and this is going to be Q0 bar, and let me treat this one as Q1 bar. That is how we are considering the flip-flop, right? Now let me write them here. In this present state, just we are going to consider, let us consider Q0 Q1, that is in the present state. Okay, now we are, next state is simply called, let us consider, let me write the next state, right? So next state in the sense we need to consider, right? So present state, next state in the sense, that is going to be Q0 plus and Q1 plus. Just we need to write present state, and from the present state we need to write next state, and then we should write the excitation table. For this we should write the excitation table, right? So that is the most important point, right? So from this we can write down the excitation table, right? So let us see excitation table for whom? T flip-flop. How many flip-flop we are going to consider? 2 flip-flops, that is T0 and T1. Carefully observe here why I am taking 2 separate bits here. Initially I understood I am in need of 2 flip-flop, right? Each and every flip-flop will having the capacity of storing only 1 bit. We all know flip-flops are what? 1 bit storage element. It means with the help of 1 flip-flop I can store only 1 bit. Whereas in order to store the 2 bits, right? In order to store the 2 bits, I am in need of 2 flip-flop, right? So here we are having 2 separate flip-flop, and the bits that we are going to store here is called Q0 and Q1, right? So let us write them. In the present state, what is the available that is possibilities, right? Present state means you can write it in the proper order. Present state might be 0 0, or it might be 0 1, or it might be 1 0, or it might be 1 1. That is called the present state of the flip-flop. Immediately the next state, right? So next state, it's only that is depending on you, right? So next state will be what? You have to bring the next state by the given sequence, right? By the given sequence. How to bring that one? Let us bring the next state. Carefully observe. If your present state is 0 0, if your present state is 0 0, then its next state it's clearly given as 0 1. If your present state is 0 0, then next state will become 0 1. Suppose if your present state is 0 1, then next state will become 1 1. Next state will become 1 1. If present state is 1 0, if present state is 1 0, present state is 1 0, its next state will become 0 0, right? If present state is 1 0, its next state will become 0 0, right? If similarly, if your present state is 1 1, then its next state will become 1 0, then its next state will become 1 0. This is how we are simply writing. See there, present state we all know, the possibility of present state is either it might be 0 0 0 1 1 0 or 1 1, but its next state will be depends, right? That is given, already it is given, right? It follows a certain pattern, right? Initially, if your first state that we are receiving in the output is 0 0, then immediately in the next stage we are going to receive 0 1, and then we are going to receive 1 1, and then we are going to receive 1 0. This is called next states, right? So the next state will be simply we are writing it with the help of what? Present state, right? So let us see the excitation table for this one, right? The excitation table, we all know the flip-flop, that is a T flip-flop excitation table, right? Now what is the excitation table for T flip-flop? Let me write it here. See there guys, there are 4 possibilities, right? So T flip-flop excitation table can be written as Qn plus 1, this is going to be T, this is 0 0 0 1, this is 1 0 1 1. For T flip-flop here 0 1 1 0, correct? This is the excitation table for the T flip-flop, right? So with the help of this one, let us consider here. Listen guys, this is present state, this is next state, that's all, right? Now we know if you are considering this one as past, then this is going to be present. If I am considering this one as present, then this is going to be future. That's all, next state, that's all. There are no more things to discuss, right? So see there, present state is Q0, next state is Q0 plus. Again present state is Q1, next state is Q1 plus. This is Q0 is meant for flip-flop T0. Q1 will mean for flip-flop T1. Clear? Okay, let us continue, right? So the journey is present state is 0, Q0, next state also will become 0. Then what is the excitation table? Present state is 0, next state also will become 0. Then its output, that is the excitation table, input is 0. Possibilities. Next, present state is 0, next state will become 1. Present state is 0, next state will become 1. Present state is 0, next state will become 1. Its possible output is 1. Present state is 1, next state is 0. Present state is 1, next state is 0. Possible output is 1. Present state is 1, next state also will become 1. So 1 to 1, possible output is 0. Let us discuss about second flip-flop, right? Present state is 0, next state is 1. Present state is 0, next state is 1, it is 1. Present state is 1, next state also 1, 1 to 1, output is 0. Present state is 0, next state also 0, for 0 0, output is 0. Present state is 1, next state is 0, 1 1 to 0, possible output is 1. Clear? That is how we are writing excitation table, right? Of course it's very easy only, right? First you have to understand. Once you understand, you can play with this one. Once you write this one, then directly you are supposed to write what? K-map, right? In order to implement this circuit, it's over, right? So let us write the K-map for T0 directly. That is, K-map means I'm in need of minterm. That is expression. I should require the expression. Okay, we are usually writing it in what? That is a sum of product, right? SOP form, right? So let us write T0. Anyway, we have only 2 minterms. Directly we can write. Unnecessarily we don't want to use K-map here. That is waste of time. Let me write for T0. Right now, while writing the what I can say minterm expression, or while finding the T0 value, you are supposed to consider present state, because that is our present state. In this state only we are going to jump to the next state, right? So while writing the characteristic equation, you are supposed to follow present state variable, that is Q0 and Q1. It means, see there, for T0 I am getting 1. Its correspondent variables are 0 and 1. It means it can be written as Q0 bar dot Q1. Can I write like this? Here I am getting minterm 1, right? 1 means its possible inputs are, right? We know how to write this one. Similarly, plus I am getting one more minterm here. Its possible inputs are going to be what? We can say that is Q1 Q0 bar. Sorry, I think this is Q0 Q1 bar, right? So Q1 bar into Q0, right? Of course, it's what? It's XOR logic, right? So we can say X1 XORed with the X0. Clear? And that is going to be the input of T0, right? So let us let us write the expression for T1, second flip-flop. Here we are getting 1. Its corresponding inputs are going to be Q0 bar dot Q1 bar, plus here I am getting 1. Its corresponding inputs are going to be Q0 dot Q1. What is this? This is XNOR logic, right? So we know this is XNOR logic, that is X1, Q1 XORed with the Q0. Q1 XORed with the Q0. We know? Yes. So finally what we have understood, we are going to consider, right? So let us take this flip-flop. Let us do the implementation, right? So finally we are going to implement the flip-flop. It's over. Okay, fine. So let me write down this circuit. Listen guys, T0. T0 is what? T0 is Q1 plus Q0, that is Q1 XORed with the Q0. Where is Q0? This is Q0, this is Q1, right? So let us take them, right, outside. Let us take them outside, right? Let me bring them here, right? Let us consider them here. And they are going to be XORed, right? This is how we are providing. This is XOR gate. XOR gate, and then it will be joined here, right? It will be directly given. This is going to be the connection for T0. Similarly, T1, that is Q1 XOR with the Q0. It means, guys, listen, this is XOR gate. Yes or no? This is XOR gate, right? Now, if I'll just take, if you are taking complement for XOR, it will give you what? XNOR, right? Just I am taking complement for this and I am just giving it here. Are you getting me? This is XOR gate. I am taking one line and I am connecting inverter such that it will become what? XNOR. See there, I am end of XNOR with what? Q1 and Q0 only, right? Anyway, since it is what? We are designing synchronous counter. Synchronous counter in the sense all the counters will be what I can say synchronized with a single pulse, that is positive edge triggering or negative edge triggering, or you can also use level triggering. It's up to us, right? Fine. So that is how we are designing what I can say circuit, that is how we are implementing the flip-flop for the random sequence, right? So for your best understanding, let me take one more example, right? So let us take the next one, right? We'll take some random sequence. Let us see how to design the random sequence, right? You can also take some another examples by yourself. You can take, right? You don't need to wait for me, right? Because it's quite interesting and it is very easy, right? The thing is, it's very easy, right? You can increase the number of bits, right? You can consider 3 flip-flop, that is, you can consider 3 bits, right? But I don't want to do that one because I don't want to waste my time, right? You will understand with the 2 bits. You can do it by yourself, right? Later you can take any random sequence with the 3 bits and you can just do it by yourself, right? So let me go ahead with the 2 sequence only. Let us consider 1 1 first state. Second state is going to be, let us consider 0 1. Next it is going to be 1 0. Then it is going to be 0 0. Right? That is the given sequence. Again it follows. Again 1 1. It repeats. Again 0 1. Again 1 0. Again it is 0 0. Under this sequence generation, this is being repeated here. Now what we are going to do, this is simply called random sequence, and you are supposed to implement this one by using JK flip-flop, right? The question is generate or design the design the counter for the given random sequence by using JK flip-flop, right? So design the counter for the given random sequence by using JK flip-flop. That is the given question, right? What we need to do, step number 1, right? We'll have to write present state and next state excitation table of JK flip-flop. That's all. Directly you can write. So let me write present state directly. Let us write the answer, right? So present state, right? So we have to write present state and then we have to write next state, right? So we have to write next state. And then we have to write the excitation table, right? We have to write the excitation table, right? So we need to write excitation table here, right? Now after writing all these things, right? So let me place the variables. The thing is, we are going to design what? JK, that is we are going to design the counter with the help of JK flip-flop, right? And let me write the excitation table later. First present state means first of all design, that is decide how many bits should be required here. See, there are 2 bits. See there, 1 1 0 1 1 0 0 0. 2 bits are there, right? Anyway, total possible combinations are what? 1 2 3 4. Again 1 2 3 4, right? In order to bring 4 states, I am in need of 2 flip-flop, right? So once again, let us consider 2 separate flip-flop, right? So first, let me consider J0 K0, and again let us consider J1 K1, right? Again let us consider J1 K1. Let's see how to design the flip-flop, right? So this given flip-flop, right? So once again, later I will draw the circuit. First let us complete, right? Again the states that we are going to consider, present state, right? So here we are going to consider what? Q0 Q1 once again this is going to be Q0 plus and this is going to be Q1 plus. That is the outputs of the flip-flops, right? So Q0 is going to be the output of JK flip-flop, J0 K0 flip-flop, Q1 is going to be the output of JK, the second flip-flop, right? Yes. So let us write the present state. The present possible states are 0 0 0 1 1 0 1 1. Now the next state, let us see. If present state is 0 0, then its next state is going to be 1 1. If present state is 0 1, then its next state is going to be 1 0. If present state is 1 0, then next state is going to be 0 0. If present state is 1 1, then next state is going to be 0 1. That is how we are writing the next state. Simply just observe the given sequence, just write it here, right? Next state, immediately we have to write excitation table, right? Now for the JK flip-flop, what is the excitation table, right? So the excitation table of the JK flip-flop is Qn plus 1 JK. What we saw, this is 0 0 0 1 1 0 1 1. Totally we have 4 possible combinations. For 0 0 we are going to get what? 0x, this is going to be 1x, this is x1, this is x0, correct? Yeah, this is the excitation table of the JK flip-flop, right? So let us consider and let me put this here. Now see there, present state is 0, next state will become 1, right? If present state Q0 to Q0, I am writing the excitation table for JK flip-flop, right? Present state is 0, next state will become 1. For 0 to 1, its correspondent value are going to be, right? Input is possible inputs are 1x. Present state is 0, next state will become 1 again, right? Present state is 0, next state will become 1, then its possible values are 1x. Again, present state is 1, next state is 0, right? Present state is 1, next state is 0, its possible output is what? x1, right? So that is going to be x1. Present state is 1, next state will become 0, again it is going to be what? Possible outputs are x1, right? So let us write the next one. Now we need to consider J1 K1, right? Next flip-flop. See there, while going from 0 to 1, once again we are going to consider what? 0 to 1. While going from 0 to 1, its possible outputs are 1x. Now while going from 1 to 0, it is become x1. Again it is going from 0 to 0. While going from 0 to 0, which is become 0x. Now while going from 1 to 1, which is become x0. Clear? So that is how we are writing the excitation table, right? So from this what I can say, given table, that is the present and next table. Once you write the excitation table, your next task you will have to write the expression for all these people, right? So let me write J0 separately, K0, J1 separately, K1 separately, right? So let us consider, for a better understanding, let me put them into K-map, right? Such that you will be able to get the clear idea, right? Yeah. Now the thing is, I said while developing the K-map, just consider the present state. Right? Now see there, Q0, Q1 is there, such that this is going to be Q0 bar, this is going to be Q0, this is going to be Q1 bar, this is going to be Q1. Let us substitute the variables for J0. First let me consider J0. This is J0. It's possible. For 0 we have 1, for 1 we have 1, for 2 we have don't care. Such that you can club all these things. So it's clearly denotes that J0 equal to 1, because all terms are grouped together such that Q1 plus Q0 bar become 1, Q0 plus Q0 bar become 1, 1.1 will become 1 only, na? So directly we can write our answer as 1, right? So similarly, see there, did you observe K0 also going to be 1 only? See there, you can directly group them, right? You can directly group them together. Quad, that is quad will be possible, right? Quad group is possible such that I can say J0, K0 both are going to be 1 only. Now let us write the expression for J1 and K1. For that, let me put them into the K-map, right? And for 0 we have 1, for 1 we have x, for 2 we don't have any variable, again we have. Anyway, grouping could be possible. This is going to be Q0 bar Q0, this is going to be Q1 bar Q1, such that if I'll group these two, what we are going to get, J1 can be written as Q0 bar, J1 can be written as Q0 bar, right? So let us consider the next one, right? The next one is what? Again we are going to consider K1, right? So for the K1 correspondent variable, see there, we have x1, we have x0. Once again we can club them together. Once again this is also going to be what? Q0 bar only, right? So here we are going to consider Q0 bar, Q0, this is going to be Q1 bar, this is Q1, such that I can say K1 also equal to what? K0 bar only, right? So what we have understood, we understood how to design the flip-flop circuit, right? So okay, these are the things that it should be required now. These things now you can remove. Finally you can just rub all these things, we can draw the circuit, right? So let me rub all those things, let us draw the circuit. You please do it by yourself, don't wait for me, because I know all of you have understand these circuits now, right? That's all. That is how we are designing a random counter. Clear? That is how we are designing random sequence, right? Yeah, fine. So our next target is we have to implement this circuit, right? Anyway, we are considering what two flip-flop. One is J0, another one is K0. Sorry, JK. Let me consider two flip-flop. JK flip-flop, that is J0 K0, and then J1 K1, right? So J1 K1. Since we are designing what synchronous counter, so all flip-flop will be synchronized together with the same clock pulse, right? And second thing is, let me consider what I can say J0. Let us consider K0, let me consider J1, let us consider K1, right? Such that this is going to be Q1, this is going to be Q1 bar, this is going to be Q0, this is going to be Q0 bar. Let us implement this circuit. J0 equal to 1. What about K1, K0? K0 also going to be 1. What about J1? J1 and K1 both are going to be connected to what? Q0 bar. This is Q0 bar, right? So it will be connected here directly. They will be connected with the J1 and K1 both are connected with the Q0 bar. This is Q0 bar. Clear? So that is how we are simply designing what JK flip-flop. That is any counter, right? So the conclusion is what? Any counter, right, can be implemented like this. Clear? Any counting could be possible. So the conclusion is what? The beautiful observation is, you are supposed to travel along with what synchronous counter, right? So the advantage of the synchronous counter is, now see there many observations we are getting here, right? The advantages is what? All flip-flop will be synchronized at the same time, right? So automatically what will happen? The error generation will be reduced. We saw, right? Starting itself I told you error generation will be reduced. That is there might be a chance of getting error when we are traveling along with the asynchronous counter. That error automatically what, it will be minimized in case of what? Synchronous counter. And since all synchronous counters are synchronized together such that it is working at a very high fast, right? Its speed is what? Very high. Let us see the comparison of synchronous counter and asynchronous counter or asynchronous counter, right? So let us see the difference between synchronous counter and asynchronous counter, right? So let us rub all these things. This is all about designing of synchronous counter, right? Yeah, random counters. Now next thing is, we need to understand the difference between synchronous counter and asynchronous counter, right? So let us see the difference, right? Let us place synchronous counter and asynchronous counter, right? Asynchronous counter. Now first of all, what is the difference between synchronous counter and asynchronous counter, right? The major difference is, here all flip-flop will be synchronized at a single clock, right? Whereas here first flip-flop, that is simultaneously. Here if you observe asynchronous counter, flip-flops are what I can say simultaneously triggered, right? That is the rest of flip-flop, this only first flip-flop will be triggered with the help of clock pulse, right? Clock pulse will going to trigger only first flip-flop, right? Whereas here all flip-flop will be synchronized together, right? All flip-flop having single clock, right? So they will have single clock. First thing, it clearly denotes that which flip-flop will work at, that is which counter will work at very fast, this counter, because all flip-flop will be synchronized, it is faster, right? Together, it means here it is slower, right? So it won't work that much faster when we are comparing it with the what I can say synchronous counter, right? So that is the next drawback. Now here in case of synchronous counter, the advantage is random sequence could be possible, that is any sequence, right? Or otherwise we can say any sequence could be possible here, right? Any sequence counter can be designed here. But here you can design what? Only up and down counter, right? We are designing here only up or down counter you can design. Guys, don't forget, in asynchronous counter we said there are two type of counter. One is binary counter and another one is non-binary counter. Even in non-binary counter also we went up with the up counting or down counting only. But the thing is what? We have not non-binary means, for an example, when we are going up with the 4 flip-flop, we can count 16 state. But we wish to calculate, we wish to count only 12 states. It does not mean that it is a random sequence. That is not random sequence. You can count all values from 0 to 12, right? But you are supposed to just stop. 13, 14, 15, 16 states are unused states. But if you observe the states, what? We have started our journey at the 0 and then 1, 2, 3, 4, 5, 6. This is up counter, proper up counter. So what is the conclusion here? So the finalized conclusion here, right? So the finalized conclusion is, when we are discussing about synchronous and asynchronous counter, in asynchronous counter we will always, that is, we will be able to design, either we can design up counter or we can design down counter. All counting sequence could not be possible here. That is the next drawback. Here there will be a chances of getting error in the coding, right? So there will be a chances of getting error in the coding, right? Whereas here there is no error. That is called a decoding error. We are simply calling them, right? So here it is no error. Here it is no error, right? And one second. Synchronous counter is simply called parallel counter, right? It is simply called parallel counter, whereas asynchronous counter called series counter, right? It is simply called series counter, right? Because see there, here all flip-flop will be synchronized together. It means parallelly we are giving input for all the people. Like the thing is, if I'll have 4 bulb here, I have 4 bulb here, I have 4 bulb here in case of parallel circuit. Now see there, when we are passing the electric current here, the thing is directly what will happen, this current will be, this bulb will consume some current, 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 such that all bulb will started glowing, that is glowing at the same time, they are glowing at the same time, right? Whereas when we are looking for series circuit, if I have a bulb like this, now what will happen, first this bulb has to glow. If it is glow, then it will allow the current to the second bulb. Suppose if there is any failure in the first bulb, automatically second bulb what will happen, it will unable to work, right? It won't do anything, because what will happen here, there will be some malfunctioning in the first bulb, right? If it is not working properly, then automatically it will spoil all the flip-flop. Clear? See that this is series circuit, right? What we saw when I was designing about synchronous counter, how we were designed. First flip-flop will be connected with the clock, whereas second flip-flop second flip-flop will be that is synchronized, or it will be triggered with the help of output of the first flip-flop. Immediately third flip-flop will going to be triggered with the help of output of the second flip-flop. It will be continuous. That is called series. Whereas in the synchronous counter, what we saw, all flip-flop will be synchronized with a single clock pulse. Clear? That is the difference between this one. So this is called a parallel. Parallel means all flip-flop will be triggered with a single clock. That is called a parallel counter. Whereas this is called what? Series counter. Of course, this is also called ripple counter. We know there is one more name for this. It is also called what? Which is also called ripple counter. Right? I hope things are very clear to you all. Right? Okay. So these are all the some of the difference between what? Synchronous counter and asynchronous counter. Okay. So with this, counter part is completely over, right? So there is one more part, right, in sequential circuit, right? So let us design that one. That is simply called registers, right? So that is simply called registers, right? So let me remove this one first. Let us discuss about registers. Keep that ding. Next we are going to discuss about registers. Of course they are called shift registers, right? We are going to design what? Shift registers, right? Now what we are going to learn in shift registers? First of all, what is the purpose of shift registers, right? So in shift registers, like assume like this, we are going to store some songs, right? Like in shift registers, we can store the bits, right? What I can say, we are going to store some informations inside the circuit, and we are also going to transmit the data from one point to another point. And we can also perform some arithmetic operations like addition. You can add two binary values, binary numbers, right? We can also perform, and we can also generate some sequence, like a sequence generator. It can also act as a sequence generator, and it will also act as a ring counter, right? So there are many applications for your shift registers, right? So with shift registers are simply called what? They are the advanced or developed version of flip-flop circuits. Actually, we know with the help of the flip-flops, what we can do, we can store the bits, because they are having memory now, right? But the thing is, when we are trying to add more number of bits or more number of informations, automatically we are modifying the circuits, or we are adding more number of flip-flop, right? And then that more number of flip-flop will going to simply act as a register circuit, right? The most wanted flip-flop that we are using in order to store the data in case of shift register is simply called a D flip-flop, right? Priority will always be given for D flip-flop. Why? Because that is a data transmitter. It will simply transmit the data. Whichever the data that I am giving, it will transmit. That is what I want. See, the thing is what? You are trying to, you would like to, hear some songs on YouTube. Just you are trying to play that. What will happen? Whichever the song that you are liking, right? So the thing is, you are looking for the searching engine. You are just going there and you are searching whichever the songs that you want. Automatically, what will happen? That search engine, it has to, right? In backup that there will be some coding, right? It has to find the correct song, right? So based on the input that you are giving, right? And it has to pick it back, and you will have to what? It has to give it back to you, right? Whichever the song that you are that you are already given that coding in terms of coding, right? That same song will going to be what? Displayed. Okay, what is the conclusion here? நீங்க என்ன கொடுக்குறீங்களோ அதுதான் அவுட்புட்ல வரணும். Unnecessary எதுவும் நடக்க கூடாது. That things could be possible with the help of D flip-flop, right? So the most wanted flip-flop, right, in case of, right, while designing the what I can say shift registers, right, the wanted flip-flop is what? D flip-flop, right? Priority will always be given for D flip-flop only, right? So let us take D flip-flop, right? I hope things are very clear. With the help of shift register, we are going to store the bits. binary bits, right? And we can also transmit the bit from one point to another point, right? And we can also convert the code like from serial to parallel code or parallel to serial code, right? So simpler, that is, people are simply calling it as temporal code and spatial codes, right? So let me teach you slowly. We'll see all those things, right? So we are going to learn about two type of code. One is called temporal code, another one is called spatial code. Actually there are no big difference, right? If you are talking about serial, that is series code, they are simply called temporal code. Parallel codes are simply called spatial codes. That's all, right? Fine. So there are four type of shift registers are there. You can register the data with the help of, that is, serial data, right? That is, there are four type of registers are there. First thing is, we are going to register the data with the help of series circuit, and we are going to collect the data in the same way, that is series, in the same way, right, that we are registering. And the second thing is, we are going to register the data in series, but we are going to collect the data in parallel. Again we are going to register the data in parallel, but we are going to collect the data in series. Again we are going to register the data in parallel, again we are going to collect the data in parallel only, right? Such that we will be able to design four type of flip-flop with the help of D flip-flop, right? That is, we will be able to design four type of registers with the help of D flip-flop, right? So the priority will be given to you, that is given to what I can say, D flip-flop, right? So let us consider first thing, right? So let us talk about shift register. We are going to design shift register, right? So shift register, it's quite interesting actually, right? What is the purpose? It will going to perform many operations, right? So first of all, we need to understand the difference between serial code and parallel code, right? Serial and parallel. Let us see the difference between serial and parallel codes, right? I said serial codes are simply called what? Temporal codes. They are called temporal codes. Similarly, parallel codes are called spatial codes, right? It means actually here what we are doing, right? So here we can transform the code, right? We can convert the temporal code as spatial code, or spatial code as temporal code. That is, first application is, with the help of a shift register we can perform, that is, temporal code can be transformed as what? Spatial code. Similarly, spatial code can be transformed as temporal code. This is spatial, this is a temporal, this is spatial, this is temporal, right? So this is the first application of your, what I can say, shift register, right? And I said apart from this, it will also going to help us to perform some arithmetic operations. You can also perform some arithmetic operations, right? So that is arithmetic operations. That means you can add binary data. That is what I would like to conclude already. And you can also generate, that is a sequence generator. It will also act as a sequence generator, right? We can generate the whichever the sequence that you want, right? Yeah, it can also act as a sequence generator. We can also design ring counter, right? With the help of this one, we can design ring counter, right? So these are all the some of the application of your shift register. Okay, fine. So let us start our journey. Now what do you see relation between temporal and spatial? Temporal means serial, spatial means parallel. That's all. So we can transform the data from serial data to parallel, or parallel to serial transformation could be possible with the help of shift register circuits, right? So now your shift register will be classified into four types, right? So that is, the thing is, one more thing you have to understand here, right? Sir, why we are giving priority for D flip-flop? Already I have been told you, right? Anyway, you might be thinking, you might be wonder, sir, is there any other flip-flop, right, in order to do the same task here? To do the same task or to perform the same operation, right? Can we use some other type of flip-flop? Of course, you can use SR flip-flop, JK flip-flop, T flip-flop. But the thing is, if you are trying to wish this circuit, that is, if you are trying to implement this circuit with the help of other flip-flop like SR flip-flop, JK flip-flop, T flip-flop, right, with the flip-flops, there might be a need of some logic gates. Otherwise you cannot directly bring these circuits, or we cannot design the circuit simply, right? So in order to implement the same type, that is in order to perform the same operations that we are going to perform with the help of D flip-flop, you can also perform it with the help of other flip-flop. But while traveling along with the other type of flip-flop, you are also required to, that is, you are also requested to consider with some logic gates with the flip-flop. So what will happen? Already in flip-flop we are having an issue that is called delay, propagation delay. If we are also giving priority for what I can say, logic gates also, first thing is cost of the circuit will be increased, because unnecessarily we are implementing, right, we are some logic gates also, right? And second thing is, automatically in the designing, right, it is not a simple designing when we are comparing it with the D flip-flop, right? So second thing is what, there might be a chances of getting delay. because of the presence of gates also, right? So in order to avoid all these issues, we are giving priority for D flip-flop. In D flip-flop, there is no need of logic gates at all. Simply with the help of flip-flop itself, we can perform the operation. Clear? I hope things are very clear now. So let us take the D flip-flop. Let us design. There, I said there are 4 flip-flops. One is called CISO. First, we are going to design serial input, serial output flip-flop, right? Sorry, register. The first register is what? Serial input, serial output register, right? So let us see the first type of register that we are going to design now is called CISO register, serial input, serial output register, right? Yeah. So the first type of register is SISO register, right? It stands what? Serial input, right? It stands serial input, serial output, serial input, serial output register. It stands serial input, serial output register. Let us see, right? For an example, let us take some 4-bit flip-flop. 4-bit in the sense we need to consider 4 flip-flop, right? So let us consider 4 flip-flop here, right? Let us see how to design this one. 4 flip-flop, right? Yeah, this is 4 flip-flop. Now what I'm going to do, I said just use what I can say D flip-flop, right? So let me consider D3, let us consider D2, let us consider D1, let us consider D0, and let me consider this one as Q3, let us consider this one as Q2, this is going to be Q1, and this is going to be Q0. Clear? Now simply just connect these two guys, connect these two guys, connect these two guys. Clear? And this is going to be the input of the flip-flop, right? So anyway, what we are going to do here, we are going to synchronize all the flip-flop together, right? So let us synchronize them. First, let us synchronize them. Let us see how we are going to transmit the data now, right? So how we are going to transmit the data now, right? So I said we are going to consider what? Serial input, serial output. Serial input, serial output means, for an example, I would like to register the data is called 1011, right? So this is the data that I would like to register into the flip-flop, right? Okay guys, listen, this is the point where we are going to collect the output. Whereas where we are going to store the bits, right? The storing position is, this is the storing point of the bits, right? You will have to store the bits at this point, right? This is called input. This is the point where we are going to store the bit. Again, input, we are going to store the bit. Input, we are going to store the bit. Input, we are going to store the bit. Clear? So first step, right? We have to register the data, right? We have to register the data. Let us see initially, right? Initially, we have not stored any data here. All are set to be 0, right? So before applying clock pulse, initially clock is 0, and the data, registered data in Q3, Q2, Q1, Q0 are 0, right? So there is no data that were registered. Now when we are giving first clock, now what will happen immediately when we are synchronizing, right, all flip-flop together, what will happen? This 0 will be transmitted here, and this 0 will be transmitted here, this 0 will be transmitted here, because this is D flip-flop, right? Simply the data will be transferred. See, their first bit will enter here, it will become here, such that what will happen in the next set, Q3 will become 1, rest of guys are going to be 0. Now let me give the second clock. Now what will happen? 1 bit already entered, right, such that this will become 1 now. When we are giving second clock, then what will happen? This 1 will be transmitted here, this 0 will be transmitted here, that 0 will be, so these two people will become 0, this 1 will be transmitted to Q2, and one more 1 will enter into the circuit, such that it will become 1100. Now see there, again we have 10. Now when we are applying third clock pulse, now what will happen? See there, before applying third clock pulse, let us see, this is 11, this is 00. Now the next thing is what? When we are passing 0 inside the circuit, then what will happen? This 1 will be transmitted here, this 1 will come here, this 0 will come here, right? So such that what will happen? Q3 will become 0, this 1 will go here, this 1 will come here, this 0 will come here. Now when we are applying fourth clock pulse, what will happen? This 0 already entered, now this will become 0, now this will become 1, yeah, this will become 1, rest of all are 0. Now last step, when we are applying fourth clock pulse, that 1 will be transmitted here, this 0 will come here, this 1 will come here, this is going to be 1. Finally we are getting 1, 0, 1, 1. See there, this is the data, right, that I would like to register into the circuit. Right? Now what I have done here, in order to register the 4-bit data, I am in need of 4 clocks. How many clocks that are required in order to register the data? See there, totally here, how many flip-flops are there? 4 flip-flops are there, right? How many bits that we are that I would like to register here? 4 bits, right? So when I am trying to register the 4 bits, I am in need of 4 clocks. Right? I am in need of 4 clocks. So what is the conclusion? From the input side, right? So the number of clocks, right? Number of clocks required to register the data, right? For 4 bits, right, the number of clocks are required to register the data in the input side. Don't forget, I am talking about input side. That should be equal to what? 4. Actually 4 clocks should be required. Let me renderize, right? Let us consider, here we are considering 4 clocks because we took 4 bits. Let us generalize. It is going to be n for n bits. It is going to be n for n bits, any bits. Clear? Now let us take the second case. The second case is, now all the data had been registered into the circuit. Now you will have to collect the data. Where is your output port? I told this is the point where we are going to collect all the data. Output port. Directly you are going to, I said we are designing what? Serial input, serial output, right? So serial output in the sense, serially we are going to collect the output at this point, right? So let us see how we are going to collect the data in the output side, right? So the case number 1, right? So initially if you observe in the output side, we are receiving only one data, right? So see there, guys, listen. To directly receive this data outside, you don't need to apply any clock pulse, because if you apply clock pulse, then the data that we are having here, it will be transmitted to the output port, but this data won't be changed. So the conclusion is what? You can directly collect this data without any clock. Are you getting me, right? In order to collect this data from here to here, this is my output port. Already this one is what? It is available at the output directly. So without applying, right, before, that is without applying any clock pulse, directly I can collect the last data. But in order to collect the rest of 3 data, right, the data that was stored into the circuit, in order to collect these 3 data, we have to apply what I can say, clock pulse. For an example, first let us discuss about output, right? In the output, already I had received 1, right? So 1 we had been received without any clock, right? So here I did not apply any clock, that is 0 clock, right? So we are in clock, that is 0 clock. Next, what will happen when I am applying the first clock, right? So when we are applying the first clock once again into the circuit, what will happen? Your data will be transmitted. It means already I had collected this one outside. Now this one will come here such that we are collecting the next data. This one will go to the output. This 0 will come here. This one will come here. Now this will become 0 once again. So see there, we are collecting the second data. Again I am applying second clock pulse. When you are applying second clock pulse, this 1 will gone, this 0 will come here, this 1 will come here, again it is going to be 0. So we are collecting the third data with the help of second clock pulse. Again when we are applying third clock pulse, automatically what will happen? This one also will come outside, such that this is the registered data and the same data that we have collected outside. Clear? So actually what I was registered here, 1011. Now first what we saw how to register the data. Second what we saw how to collect the data, right? So if you observe the output side, in order to collect, right, in order to collect n bits or 4 bit, how many clocks are required? 3 clocks. Why? Because in case of serial output, already 1 bit is readily available in the output side. So in order to collect that 1 bit, we don't need to apply any clock pulse. So the conclusion is, in order to collect, right, so in the output side, let me write number of clocks in the output side. Number of clock is only 3 for 4 bits, right? Only 3 to collect 4 bits, right? Then it will be n minus 1 for n bits. Getting me? It will be n minus 1 for n bits. For 4 bits, it will be 4 minus 1. That is equal to 3. For n bits, it will be n minus 1. Clear? So that is how we are finding the number of clocks also. Don't forget, you will be tested with some worthless one more question. If you don't remember these formulas at all, okay, almost, though you are not remembering these things, you can done this one in your examination also. You can bring the answer directly. Anyway, just to try to understand and keep these things in your mind, right? You know how to calculate the clocks at all now. Clear? So this is all about serial input, serial output date. What I can say, register. Now let us moving on to the next type. Let us take the next one. Now we are going to let us take serial input, parallel output, right? So let us consider serial input, parallel output. Yeah. One second. Next, what we are going to do now, we are going to design serial input, parallel output. That is serial input, parallel output, right? You can, for time being, I'm not writing the extension. You can just do it by yourself, right? Once again, let us take 4 flip-flop, right? We are supposed to consider 4 flip-flop, right? Once again, okay, let us consider 4 flip-flop here. Of course, it is over. Let us consider 4 flip-flop. Fine. Now in this 4 flip-flop, what we need to do, we have to apply once again serial input, parallel output. Serial input means data will be registered as serial only, right? So let us consider D3, and this is how we are going to register the data D2, this is D1, and this is going to be T0. There will be no changes. Again, this is going to be Q3, this is going to be Q2, this is going to be Q1, this is going to be Q0 only. So serial input, it means data will be registered serially, but the output is called what? Parallel output. It means the output that we are getting here, it will be directly collected here. The output that we are getting here, directly we are going to collect here, directly we are going to collect it here, directly we are going to collect it here. Clear? So parallel output in the sense, அங்கங்க உங்களுக்கு வர output அப்படியே நீங்க வெளில எடுத்துக்க போறீங்க அர்த்தம். You don't need to wait. இங்க போய்ட்டு நீங்க வெயிட் பண்ணனும் அவசியம் கிடையாது. This is called parallel output. We know the meaning of parallel, right? அந்த சர்க்யூட்ல இருந்து தனித்தனியா, லைக் இப்போ நம்ம என்ன பார்த்தோம்? Synchronous counter is simply called what? Parallel counter. Why? Because all flip-flop will be separately synchronized with a single clock. Right, a common clock will going to be what? Triggered all the flip-flops. See there, similarly what we are taking, right? So commonly we are taking the output from this flip-flop output can be taken separately, this one separate, this one separate, this one separate. That is called what? Parallel output, right? So let us start once again. Let us take the same data for a better understanding. Now what we saw, in order to register the data serially, already we know what will happen. So in last case also we had been observed this one clock, and we need to consider Q3, Q2, Q1, Q0, right? So before applying clock pulse, all the outputs are assumed to be 0. While applying first clock pulse, first data will enter into the circuit, rest of values are 0. While applying second clock, what will happen? Second data will enter such that this one will go here, next one will enter into the circuit, rest of people are going to be 0. That is, this 0 will go here, this 0 will go here. Again, while applying third clock pulse, what will happen? This one will go here, this one will come here, this 0 will go here, next data will enter into the circuit, that is 0. Fourth clock pulse, again this 0 will go here, one will enter, again 1 1. Clear? This one will go here, this one will come here. So how many clocks it should be required in order to register the n bit data, right? In order to register the n bit data, how many clocks should be required? I mean need of n times of t clock, right? So we can define, guys, I forgot to keep t clock in the last cases also. That is just time will be given just to multiply by n, that's all, right? So the total clock pulse that it should be recorded in order to trigger the circuit, that is n times of t clock. Clear? I hope things are very clear, right? For to you all. Now what is our next case, right? Now we need to discuss about the output, right? So how many clocks should be recorded here? Here we have to give how many times we have to provide this clock. Here we have to n times we have to, it means n times. Don't think that, don't multiply your, what I can say, if 10 is given, number of bits on the 4 இருக்குனா 10 4 ஆல மல்டிப்ளை பண்ணி 40 clocks னு கொடுத்துறாதீங்க, right? It is wrong. Actually it means what? You will have to apply n times, right? N times you have to apply the clock, right? One time, second time we have to trigger, third time we have to trigger, fourth time. That is what I mean here, right? Fine. So this is for n bit we have to apply n clock. In case of input, the conclusion is in order to register the data serially. But see there, once your data will be registered, then here you will have 1 0 1 1, correct? டேட்டா இங்கே எப்படி தானே இருக்கும், கரெக்டாக 1011 அப்படிங்கிற டேட்டா தான் நீங்கள் ரெஜிஸ்டர் பண்ணி வச்சிருக்கீங்க. நவ் ஐ வுட் லைக் டு கலெக்ட் தி டேட்டா, ரைட்? நவ் டெல் மீ ஹவு மெனி கிளாக்ஸ் it should be recorded in the output side, how many clocks are recorded in this circuit in order to collect the data. Clock will be given like this. Tell me how many clocks should be recorded. See there, we are taking the output here, Q3 we are collecting it here, Q2 we are collecting it here, Q0 Q1 we are collecting it here, Q0 we are collecting it here. See there, already data is available here. This data directly you can take, this data directly you can take, this data you can directly take, this data you can directly take. Is there any need of applying clock pulse? What is the purpose? If you apply clock pulse, then if you have any data here, that data will be transmitted, right? In order to collect this data directly, I don't need to apply any clock pulse. So what is the conclusion, right? In case of serial input, parallel output, the number of clock pulse that it should be required to collect the output is 0, right? So the number of clock pulse will be what? Please wait a minute. Yeah, the number of clock pulse is 0, right? So there is no need of clock pulse in order to collect the output data when we are discussing about serial input, parallel output. Clear? Don't forget, you will be tested for some worthless chili mark, that is 1 mark questions, right? Yeah, fine. Let us design the next type. This is serial input, parallel output register. Next let us design parallel input, serial output, right? So let us discuss about parallel input, serial output, right? So let us remove these things first. One second. Now you can try by yourself also, right? Because I hope you all have understand how we are designing the circuit, right? I hope you all have understand, right? So let us continue. Next we are going to design what? Parallel input, serial outputs. So let us design the next one, which is going to be what? Parallel, right? So that is parallel input, right? That is parallel input, serial output. So we are going to design parallel input, serial output. It means its extension, what it is simply called, parallel input serial output circuit. Clear? Yeah. So what we are going to do now, once again, let us take 4 flip-flop, right? So let us consider 4 flip-flop here. Let us consider 4 flip-flop, right? The simple flip-flop is what? D flip-flop. In order to transmit the data, we can simply use D flip-flop, right? Fine. So once again, we need to consider a D3, D2, D1, D0, Q0, Q1, Q2, Q3. Correct? Of course, all flip-flop will going to be synchronized together. Yeah, such that we can synchronize them together. What is our next task? Let me connect them. See, first of all, we are going to give parallel input. Parallel input in the sense, input for this flip-flop will be directly given from here. Input for this flip-flop will be directly given from here. Input for this flip-flop will be directly given from outside. Input for this flip-flop will be directly given from outside. அப்படியே நீங்க ரெஜிஸ்டர் பண்ணிக்கலாம். But serial output means we should connect like this. Let me join, and this is the point we are going to connect the output. This is our output. Serial output means at the MSB last flip-flop from here, right? So you'll have to observe from here, right? In the rightmost flip-flop, right? That is the output of the rightmost flip-flop is going to be the total output. That is called serial output, right? So what is the thing? The thing is, see, let us take the same data 1011, right? I have the data. Now this data waiting here. This 0 will enter here, this 1 will come here, this 1 will come here. But this is not the storing point. Which is the storing point, right? I am having the data at the input port. If you want to store the data, you will have to pass it to the edge of the flip-flop. You will have to transform it to this point, such that how many clocks should be required in the input side? Just test it now. Initially there is no clocks. Now when I am applying the first clock, right? First clock apply panna enna aguna, this 1 will be transformed to this point, this 0 will be transformed to this point, this 1 will be transformed to this point, this 1 will be transformed to that point. Clear? Such that what will happen, this 1 will come here, anyway this is going to be 0, this 0 will come here, this 1 will go here, this 1 will go to the output port. Clear? I would like to register 4-bit. Of course now it is registered. See there, this 1 is being registered, this 0 will be registered, this 1 will be registered, this 1 will also be registered. How many clock I took here? Only 1 clock. Only 1 clock. So what is the conclusion? In case of parallel input, right, wherever you can generally write this statement now. See there, for parallel input we need 1 clock, parallel output 0 clock. Last case what we saw, when I was discussing about the last case, we took serial input, parallel output. In order to collect the data parallelly, there is no clock should be required, but parallel input 1 clock should be required. Clear? Just to compare, just to remember like this, right? Okay, so here there is parallel input, 1 clock should be required. What about the serial output? Already we had been observed. In order to collect the data, serial output in the sense n minus 1 clock should be required. Do you all agree with me? Yes, already we saw first case, serial input, serial output, right? Serial input in the sense n clock should be required, right? In case of input we need n clock, whereas in case of output we need n minus 1 clock. Correct? You can also check it now. See there, how many data will be there? 1 0 1 1, totally 4 bits are there. Already we had been received this bit outside. Now in order to collect the rest of 3 bits without any clock, I had been received only 1 data. Now when we are applying the first clock, this is 0 clock. While applying the first clock, let me consider like this. This is going to be clock only. So let me consider this is going to be clock. With the 0 clock we are collecting the first data. When I am giving the first clock, what will happen? While giving the first clock, this 1 will be transmitted to the output port, such that we are also collecting the second data. This 0 will come here, right? This 1 will come here, this will be 0. Now while applying the second clock, what will happen? This 0 will coming outside, such that this 0 will go outside, this 1 will come here, this will be 0. Now while applying third clock, what will happen? 1 will also will come outside, right? 1 also will come outside, such that we are collecting the data. How many clocks we are applying? 3. How many bits we are collecting? 4. So what is the conclusion? N minus 1 clock should be required to collect the output. So the conclusion is what? Generally we can write these statements, right? For serial input, right? So first thing is, for serial input, the general case is, for serial input I am in need of n clock to register the data, right? For serial output, right? For serial output I am in need of n minus 1 clock to register the n bits. Whereas for parallel input, what we had been observed, for parallel input I am in need of only 1 clock. Only 1 clock should be required. Whereas if I am discussing about parallel output, right? If you want to talk about parallel output, let us consider for parallel output. So let us consider for parallel output what we are going to do. See, this is one clock. Parallel output, there is no need of clock. This is zero clock. Clear? So this is how we are understanding these things basically. Clear? I hope things are very clear. This is all about parallel input, serial output. So let us consider the last circuit, that is called what? Parallel input, parallel output register. Right? So let us remove this one. So let us design the last flip-flop. Last register. That is our parallel input, parallel output register. That is parallel input, parallel output register. Right? Simply you can design by yourself also. Right? I hope you all have understand. So let us discuss about parallel input, parallel output register. Right? So parallel input, parallel output. Once again, we need to consider 4 flip-flop. Right? Just for an example, I am taking 4. Right? It is not necessary that we need to consider 4 flip-flop here. Right? Let us see parallel input in the sense. Once again, let me consider the data here. D3 Q3. This is D2 Q2. This is D1 Q1. This is going to be D0 Q0. Clear? Now parallel input in the sense input will be given like this, input will be given like this, input will be given. Let us take the same data 1011, the example. Clear? Parallel output, directly you can collect the data, directly you can collect, directly you can collect, directly you can collect. Anyway, flip-flop will be synchronized together. This is synchronous counter. Synchronous register, right? Okay, clock is being applied here. Clock is 1 second, wait a minute. Right, your flip-flop will be synchronized together with a common clock, right? There is no doubt, like your synchronous counter, right? Fine. That is what I had been told you. In synchronous counter, we design a counter is called ring counter. That ring counter could be possible with the help of shift register. So shift register can also act as a ring counter. Ring counter is known as synchronous counter. So it can also act as a synchronous counter. Clear? Okay, fine. Let us continue our journey. See, listen guys. Parallel input. For parallel input, how many clocks should be required? Only one clock. Because see there, the data is available ready. It is ready-made, right? So they are readily available at the input port. If you are giving one clock, automatically this data will be shifted here. This 0 will come here. This 1 will come here. This 1 will come here. Registered. That's all, right? So with the help of only one clock, right? Only one clock, data will be registered input side. Now, what about the output? Do you want to apply any clock? No. Why? Already it is available. See there, it is in the output only. Directly we can take, it is in the output only. Directly we can take, it is in the output only. Directly we can take, this is also available in the output only row. So, in the output side, right, so the number of clock is 0, right? So, we no need to apply any clock in the output side to register the data. Clear? So, this is all about registers, right? Already we saw the applications at all. Clear? I hope things are very clear to you all. Okay. With this your sequential circuit is completely over, right? So let us solve some problems, right, based on the sequential circuits, right? Fine. So let us take some examples. Let us see them. 1 second. Okay. Let me take the first question. The question is for the ring counter given it is, right? So let us design the circuit first. They are given 4 flip-flop, right? The question is first let me complete the circuit. 4 flip-flop were given, right? It is given it is, they said there are 4 flip-flop, right? Yeah. So let us connect like this. And this 4 flip-flop had been synchronized together, right? It has been synchronized together. Yeah, it will go like this. It will be synchronized together, right? Now the question is what actually this is, they said I think D3, yeah, same, they are following like this, D2, D1, D0. This is going to be Q3, Q2, Q1, Q0, right? Now it will be simply connected like this. It will be simply connected like this, right? And they took a line here from here, and they are taking one more line from here, and they are taking one more line from here, and it will be connected with the R, that is NOR gate, I think that is NOR gate, and it is given like this, right? Now the given question is, the question is for the ring counter shown in the figure, find the steady state sequence, right? If the initial state, right? So they are given the initial state. Listen guys, the given order is Q3, Q2, Q1, Q0. They said 1110, right? Initial state is given. This is the initial state, and the question is for the given ring counter, find the steady state sequence if the initial state of the counter is 1110. Actually the question is what, for not find, actually we have to find out the mod of the counter. You are requested to find out the mod of the counter, right? What is the mod of the counter? That's all. Don't write anything, right? Given it is what, it's a ring counter, right? With the initial state is 1110. Find out the mod of the counter, right? That's all. Shall we start our journey? Initially we have to register 1110. That is the initial state, right? Okay, let us collect the data here, right? Q3, you can actually usually while counting the data, we are trying to write these statements, that is the sequence from Q0, Q1, Q2, Q3. That is the order. If you want to write it in the standard order, you can write, but I don't want to know that one here, right? Our intention is not that one. We need to find out the number of states only, right? Anyway, without applying clock pulse, 0 clock pulse. At 0 clock pulse we have what? Already data is given. For Q0 we have to reverse the data now. 0 1 1 1. Clear? That is what it was given. Now let us see while applying first clock pulse what will happen. Anyway, before applying the clock pulse we have to understand one thing here. This 1 1 1. Now what will happen? Anyway, all are going to be 1. In case of NOR gate, if all inputs are going to be 1, right, then what will happen? Output of the NOR gate is going to be 0. Do you all agree with me? So 0 is waiting here. Here we have 1 1 1 0. Now while applying the first clock pulse, this 0 will be transmitted here, right? Where it will go? For Q3, 0 will be, right? Q3 will become 0. Right, such that what will happen, this one will be transmitted to Q2, right? You can just reverse, right? This one will come here, this one will come here, this one will come here. Just you have to do like this, just you have to do like this, because I had been reversed the sequence. Now while applying second clock pulse, anyway before applying the clock pulse, let us register the new data. For Q3 we have 0, for Q3 we have 0. Anyway, rest of all are going to have 1. Rest of all are going to have 1. Now what will happen? Once again see there, 0 1 1 0 1 1. Anyway, for NOR gate what will happen? 0 1 1 also what? NOR gate output is going to be 1 when all inputs are going to be 0. That is the one and only possibility. For rest of all cases, output will be 0 only for NOR gate, right? So for 0 1 1 also, output of the NOR gate is 0 only. So what will happen while applying the second clock pulse? Once again Q3, right? So 0 is entering here. We are injecting Q3 such that already the available data will be transmitted to this point. This data will be transmitted to this point. This data will be transmitted to this point. Clear? Now let us apply the third clock pulse. Now before applying third clock pulse, let us register. The new data are 0. This is going to be 0. Rest of guys are having 1 1, right? So let us see. This one is here. This one is here. This 0 zeros are available here. Anyway, 0 0 1 also will produce what? 0 only, right? Once again output will become 0 only. Now while applying the next clock pulse, this will become 0. This 0 will be transmitted here. This 0 will be transmitted here. This 1 will come here. This 1 will come here. Once again, this 1 will come here while applying third clock pulse. Now what happens, right? So we need to apply, that is the first clock pulse, second clock pulse. Now while applying the third clock pulse, this is the data, right? Now while applying the fourth clock pulse, now before applying the fourth clock pulse, let us check the status. See there, for Q3 we have 0, for Q2 we have 0, for Q1 also we have 0. This is the only person having 1. See there, 0 0 0 will be entered here, right? If all are going to be 0, automatically output will become 1. So 1 is waiting now, 1 is waiting now, such that while applying the fourth clock pulse, this is become 1. This 1 will be transmitted here, this 0 will be transmitted here, this 0 will come here, this 0 will come here. Again we are going to get what? 0 0 1, right? So next what we are going to get while applying the fifth clock pulse. Let us see. Anyway, what will happen? 0 we have 0 0. For Q3 we have 1. Once again for Q3 we have 1. Right, for rest of all we are having 0. See there, 1 will enter here. Anyway, what? 1 0 0 will produce out 0 once again. 1 0 0, right? If at least you will find one high enable input, automatically output will become 0 for NOR gate, right? So 0 will enter once again. Now while applying the fifth clock pulse, what will happen? Let me write the sequence first here. This is going to be clock Q0, Q1, Q2, Q3. Now while applying the fifth clock pulse, what will happen? Once again, what data will enter? 0 is entering inside the circuit such that Q3 will become 0. The data that we are having in Q3, that will be transmitted here, and then 0 will be transmitted to this point, this 0 will be transmitted to this point. Now if you observe, while applying the sixth clock pulse, before applying it, Q3 will become 0, yes. this will become 1 now. Anyway, what will happen? 0 1 0 will produce once again 0 only, na? So again what will happen? 0 will enter, this 1 will come here, this 0 will come here, right? That's all, right? So wait a minute, I think somewhere I made mistake. 0 is entering here, right? So this 0 will come here, this 1 will come here, this is going to be 0. Now while applying the 7th clock pulse, once again what we have understood, for Q1 we have 1, rest of guys 0. So what? 0 0 1 will produce once again 0 only, such that next again 0 will enter here, this 0 will come here, this 0 will come here, this 1 will come here, right? Is that our data is being repeated anywhere? No, yes, we found it actually, right? Okay, fine. 1 1 0 0 and we are getting 1 0 0 and then we are getting 0 0 1. No, yeah, we are getting 7th data, again it is become 1 0 0, right? Okay, let us continue. Let me consider one more state, right? 8th clock pulse. Let us see what will happen. Now what happened? Q1 Q2 Q3 all are going to be 0 once again. Now all are become 0 and output is going to be 1. See there guys, that same state we are getting this state again, right? We are getting this state again. Now what we have understood here, initially they had registered some random data, but actually what your counter will do, your counter will state, see there, it will count 0 0 0, this is the original data, it will count this one and it will count this one, this one, this one, again same data will be repeated again. See there, 1 2 3 4, right? Only these 4 states it will going to count here, it will going to count only 4 states. Clear? So what is the conclusion here? Rest of states we are same data will going to be repeated again and again, again and again, it will going to count the same data, right? See there, you can also observe here, இதுக்கு முன்னாடி இங்க என்ன data வந்திருக்கு பாருங்க, 0 1 1 and then 1 1 0 and then 1 1 0 0 and then see there we are getting back to our original state, right? That is, this is our original state, and then same data is being repeated, same data is going to be repeated again and again, again and again, you can observe the same data in the output side. Clear? So that is how we are getting the number of states or mod of the counter. Okay, I hope things are clear to you all. Okay, let us take the second example. Next question is, write down, the question is the frequency, please write down the question, the frequency of the clock signal, right? The frequency of the clock signal, the frequency of the clock signal applied to the racing edge triggered D flip-flop, applied to the racing edge triggered flip-flop, right? Then a racing edge triggered, racing means we are going from 0 to 1, right? So racing edge triggered flip-flop, right? I'm repeating once again, the frequency of the clock signal is applied to the racing edge triggered D flip-flop. Once, wait a minute, see. Again here it is raining, right? Sorry guys, I know I'm wasting our time, right? But I don't know what to do. Once again here it is raining, right? Chillness, it's freezing, right? Yeah, fine. Let us take the question. The question is, what the frequency of the clock signal applied to the racing edge triggered D flip-flop as shown in the figure is 10 kilohertz. It means input frequency is given as 10 kilohertz. Clear, right? The frequency of the the frequency of the clock signal applied to the racing edge triggered. Racing edge trigger in the sense while going from 0 to 1. This is called racing. So they are indirectly talking about positive edge triggering, right? They are talking about positive edge triggering, right? So racing edge triggered shown in the figure with the what? 10 kilohertz input frequency. Now the question is, the frequency of the signal available at Q is dash. Let me draw the circuit first. The frequency of the circuit available at Q, right? Okay, first of all, this is going to be output port, right? Whereas they are applying the clock pulse here. This is the point, there we are going to apply the clock pulse, and the data is given as this is the D flip-flop and it will be connected with the Q bar. This is going to be Q bar, this is D flip-flop, right? So let us draw the output waveform first. Assume initial state is 0. Initial state is 0. Let us draw the input clock first. Input clock, right? So the question is what? Output frequency, and we all know how to find out the output frequency. For that I am in need of input pattern, that is clock pattern first. given it is what? Positive edge triggering. It has been clearly defined already, right? So let us draw the waveform of the output. You please do it by yourself because we know how to do, right? We know how to perform the operation. So let me draw the output waveform. Initially I am assuming the data is 0 here. If it is 0, then here it is going to be 1, then this 1 will come here. Now anyway, positive edge triggering. Now while applying the first clock, what will happen? Automatically this 1 will be transmitted to the output port such that this 0 will be transmitted as 1 and it is continuing as 1. Now if it is 1, then what will happen? Automatically it will become 0. Once again 0 will come here. Now while applying the next clock pulse, again it is shifting its value from 1 to 0. Again what will happen? If it is 0, then it will become 1. So 1 will come here. Once again while applying the next clock pulse, it is going from 0 to 1. It will be continuous, of course. Now the question is what? This is our output waveform. Its frequency is what? Now if you carefully observe, this is one complete cycle in the output waveform. What is the period of your complete output waveform? Period of the output waveform is just to consider one periodic cycle, right? If I am just comparing it with the clock, see there, to complete, right? While completing one cycle in the output port, we are completing 2 cycles in the input clock. Clockly we are completing 2 cycles. See there, 1 cycle and 2 cycles. So the output T0 is going to be what? Twice of T clock. Do you all agree with me? T0 is going to be twice of T clock. Then what about the frequency, right? If your time is doubled, then your frequency will be what? Reduced. That's all, right? So if time will increase, automatically frequency will decrease because both are reciprocal to each other, right? Since your time period is doubled, because to complete one cycle I am taking twice of clock frequency, that is clock time. So if frequency is what, then output frequency will become input frequency divided by 2. Why? Because time is doubled, then frequency will be decreased. The same proportion, right? Same proportion, because they are reciprocal to each other. What about the input frequency? Given it is 10 kilohertz, 10 by 2 kilohertz or 5 kilohertz. The answer is what? 5 kilohertz. That is the correct answer. See, your questions are always very simple. I told you, na, right? You will never face such type of what I can say analytical questions, like you have to analyze the theory and you have to understand all blob stories. Without knowing that story, you cannot solve the problem. Such a type of question never exists in digital electronics. Once you understand, you can play with your questions, right? Whichever this, what you have to understand. You have to understand the operation, right? Then it will become pretty simple, right? You can play with your questions. It's like a game, right? Because it is digital only, na. Questions are always very simple. Fine. So let us consider the next question. 1 second. The question is, the digital circuit is shown in the figure. Oh, wait a minute. Actually what they told, implemented. Guys listen. No. Please don't write down the question. The question is an XY flip-flop. Please write down. Actually I have seen some other statement. An XY flip-flop, right, whose characteristic table, right, an XY flip-flop whose characteristic table, an XY flip-flop whose characteristic table given below, right, an XY flip-flop whose characteristic table given below, whose characteristic table given below, he is to be implemented, he is to be, right, he is to be implemented by using JK flip-flop, right? It is to be implemented by using JK flip-flop, right? By using JK flip-flop. It is to be implemented by using JK flip-flop. This can be done by making. This can be done by making, right? So this can be done by making. This is the question, and they are given the characteristic table of the flip-flop is clearly given, that is X, Y, and they said that is going to be Qn plus 1, and its correspondent they have 0 0 0 1, I think same possible combinations 1 0 1 1, and its correspondent table is 1, which is Qn, and this is Qn bar, and this is going to be 0, right? And they are given 4 options, right? In option A they said J is equal to X and K is equal to Y bar, and in option B they told J is equal to X bar, right? So let us consider J is equal to X bar and K is equal to Y, and option C they told J is equal to Y and K is equal to X bar, Option D, they told J is equal to Y bar and K is equal to X. Okay, these are the four possible combinations that they had given, right? Actually, what is the question here? The question is, an XY flip-flop characteristic table is given, right? Given below is to be implemented. It means we are going to implement XY flip-flop by using what? Which flip-flop we are going to use? JK flip-flop. We are going to use JK flip-flop, right? So the conversion is, the using flip-flop is JK and the implementing flip-flop is XY. And we know the procedure. How will you perform? Step number 1, we have to write down the characteristic table for the flip-flop that we are going to implement. Correct? Yes, the characteristic table for the flip-flop that we are going to implement. 0, 0, 0, 1, 1, 0, 1, 1. Clear? It was given already. 1, which is Qn, and this is Qn bar, this is 0. Step number 1, we have to write down the characteristic table for the implement, that is a flip-flop that we are going to implement. Step number 2, we have to write down the excitation table for the flip-flop that we are going to use. Which flip-flop we are going to use? JK flip-flop, right? So we have to write the excitation table for the flip-flop, that is the flip-flop that we are going to use, right? So how will you write down the excitation table, right? In order to write down the excitation table, right? So let us consider. Anyway, what it was given here, the given it is this is the characteristic table, right? So they are considering XY here. The probably, listen guys, with this okay, let me extend this one because we need what I can say, Q&A also should be required, na? So let us extend our discussion first. Wait a minute, I did not notice that one, right? Okay, first we will remove this one because we need Qn and Qn plus 1, but they are not given Qn here, but given but indirectly given. See that this data is given here. Let me extend. This is X, Y. Let me consider Qn, and this is going to be what? Qn plus 1. Characteristic table, proper characteristic table, right? So let us write 0, 0. It might be 0, 0, 0. It might be 1, 0, 1. It might be 0. For 0, 1, it might be 1. For 1, 0, it might be 0. For 1, 0, it might be 1. For 1, 1, it might be 0. For 1, 1, it might be 1. There are 4 possibilities for Qn. Let us write the, what I can say, characteristic table properly, right? So with the given data for the XY flip-flop. If your input is 0, 0, irrespective of the Qn, output is 1. If your input is 0, 1, it will follow Qn. Qn is what? Qn is 0. Here Qn is 1. If your input is 1, 0, then output is Qn bar. If it is 0, it will become 1. If it is 1, it will become 0 because Qn bar. When your input is going to be 1, 0, output will become what? Qn bar. That is Qn plus 1 will become Qn bar, right? When your input is 1, 1, irrespective of the past, output will be 0. That is how we are bringing characteristic table. Now once you bring the characteristic table, then automatically you can write the next task is excitation table, right? So let us write the excitation table. J, K. Shall we write? Yes. JK flip-flop, right? So excitation table, when we are giving 0, 1, so first let me write them here. JK flip-flop can room for 0, 0, right? We have 0, 0, 0, 1, 1, 0, 1, 1. This is going to be what? 0x, and this is going to be, I think, wait a minute, this is 1x, this is x1, this is x0. Clear? This is the excitation table. Let us see when it is 0, 1, right? 0, 1, this one. It is going to be what? 1x. Now when it is 1, 1, it is going to be what? x0. When it is 0, 0, this is going to be 0x. When it is 1, 1, this is going to be x0. When it is 0, 1, 0, 1 means it will be 1x. When it is 1, 0, it will be x1. When it is 0, 0, it will be 0x. Correct? When it is 1, 0, 1, 0, it will be x1. It will be x1. That's all. Right? Now we have to implement it into the K-map. Right? So we have to put them into the K-map in order to find out the solution for this. Right? So let us consider 8-cell K-map 1, 2, 3. Right? So let us place the variables. We need to consider x, y, qn, right? So such that let me consider x bar x. Let us consider y bar qn bar, y bar qn, y qn. Last one is y qn bar. Let us substitute the variables. I am writing K-map for j, this table alone. Let us register the values 1, 2, 3, 4, 5, 6. I think 0, 0, 1. 2, 3, 4, 5, 6, I have 0, right? Now we have see that directly we can club them, right? So 4 quad could be possible such that what is the value of j? J is equal to x plus x bar become 1. Automatically here what is the common value? Y bar is the common value. So j is equal to y bar, first conclusion, right? How many options are there? Automatic. Actually, we have only one option, na? Anyway, let us take the next one also. We let us put them into the K map. Yeah, 1, 2, 3. Right. So again, same variables. X bar x. This is y bar qn bar. This is y bar qn. Y qn. This is y qn bar. Substitute பண்ணலாமா என்ன பாருங்க 0 1 2 0 1 2 3 4 5 6 7 no this is 6 this is 7 yeah anyway what is the conclusion here we should club them together 4 quad could be possible no yeah that is quad could be possible so directly what is L of k which will be equal to only x because all this possibility எல்லாத்தையும் ஆட் பண்ணீங்கன்னா 1 வந்துரும் right so what is the conclusion k is equal to x j is equal to I told you when I was doing the conversions in your examinations will be tested with some general circuit see that this is general flip-flop they are implementing general flip-flop only so you'll have to remember the conversion procedure that is very important clear because you'll be tested for this type of worthless 2 more questions yeah next let me take the next one yeah please wait a minute yeah it's over I'm done next the question is in the figure right in the figure as long as x1 equal to 1 as long as x1 equal to 1 and x2 equal to 1 as long as x1 equal to 1 and x2 equal to 1 the output q remains the question is the output right the output q remains right the output q remains right so let us consider the given circuit right so let me consider the given circuit this is q naught that is an AND gate they had given actually and they are considering one more gate here 1 second let me complete yeah I think that is AND gate right yeah this is AND gate and here they are considering this one will be connected here right so this one will be connected here and they said this is called q right and the inputs is given as this is going to be what x1 this is x2 actually question itself that is given now yes they are given 4 values right option A this is 1 option B that is 0 option C at initial value option C at initial value at initial value option D unstable right they said unstable option D they said unstable right okay shall we start yes let us perform our operation now it is clearly given that these two values are as long as 1 means it is permanently fixed as 1 now the output of this function is hardly depends on the initial output right for an example initially let us assume this value is q right so let us consider if inga q வந்து either it may be 0 or 1 I don't want to consider directly it be considered q appo q inga varuma this q will come here this is NAND gate output of the NAND gate is what 1 dot q that is going to be 1 dot q whole bar that is AND gate dot b whole bar that is NAND gate output such that q bar will enter at this point what is the AND gate what it will do right so this is the initial state now in the next state let me consider q dash let us see what will happen right or let us consider initially let me consider q naught such that we are treating this one as q naught next state let me take this one as q1 let's see what will happen q naught bar with 1 once again what will happen 1 dot q naught bar such that your output is what q naught bar complement of the initial value right so complement of the initial value in the sense what do you mean I hope you all remember when we were designing the JK flip-flop when we have designed the JK flip-flop in the output state of the JK flip-flop we saw there are 4 states for 0 0 0 1 1 0 1 1. We saw the truth table of the JK flip-flop, which became, that is Q1. This is 0, this is 1, and this became as Q1 bar. What is this? This is called race around condition. I told you this state is called unstable state. This is called a toggling state. Unstable in the sense your state is not stabilized. It means if it is 0, next state will become 1. If you are considering 1, next state will become 0. See, Q bar means what it indicates. Initially if it is 0, next state will become 1. Suppose if it is 1, next state will become 0. Again it will be repeated. No? If it is 0, next state will be the complement of this one. Again if it is 1, next state will be the complement of this one. It means 1 0 0, again 1 0 0 1, 1 0 0 1, 1 0 0 1. Toggling state is what? Unstable state, right? It is neither 1 nor 0, right? Initial value லையும் கிடையாது, right? Initially நம்ம 0 அசைன் பண்ணா எனக்கு காம்ப்ளிமெண்ட் ஆகி தான் வருது, அதே வேல்யூ வரல, right? So the correct answer is unstable. Okay, fine. Let us consider the next one. Please wait a minute. Sorry for the interruption. Yeah, that's fine. Next, what we are going to do? Let us consider the next one, right? Okay. Next one is the circuit is given as I hope you all will figure out this circuit. That is the given circuit. Actually, the question is, in the circuit, the race around, right? In the circuit, the in the circuit, the race around, that is all. They are given 4 options, right? Option A they told does not occur. Option A they said that is. Can you please post your answer? Right, I am just expecting your answer. You can post your answer in the comment section. Option B occurs when clock is 0, right? Occurs when clock is 0, occurs when clock is 0, occurs when clock is 0, right? Option C occurs when clock is 1 and AB equal to 1, occurs when clock is 1, when clock is 1 and A and B are equal to 1, A and B are equal to 1, right? So option D occurs when, wait a minute, occurs when clock is 1, right? When clock is 1 and A and B are equal to 0, A and B are equal to 0. Can anyone post your answer in the comment section? It is very simple question. Question is what? Race around condition எப்ப நடக்கும்னு கேட்டிருக்காங்க. That is the question. First of all, we heard a term is called race around in which flip-flop? JK flip-flop. Yes or no? Of course, we can. That is the one and only flip-flop. There we are observing JK, that is the race around condition. Do you all agree with me? Yes. Now, what type of flip-flop that is given to us? If you observe, this is the layout of SR flip-flop. You can find out the truth table. In SR flip-flop, do you have any race around condition? No. I have what? What I can say, unused state, right? So there is a term is called don't care, right? So in SR flip-flop, already we design for RS flip-flop only we design the output Qn plus 1. Actually we saw what? 0 0 0 1 1 0 1 1. For this we got what? Qn 1 0. Here what we got? Here we got don't care, unused state. So here we got unused state. We never touch what race around conditions at all in SR flip-flop. Of course, it is possible in JK flip-flop, right? But it is not in SR flip-flop, right? So what is the correct answer? Does not occur, right? So given it is SR flip-flop, so there is no point of discussing about race around conditions at all, right? That is wrong. Let us discuss about the next one, the state transition diagram. The next question is state transition diagram is what? That is the question. Let us see. this is d flip-flop q bar, which will be given to mux. That is, they said this is x1, this is x0, and this is a, and this is y. Here they are giving clock pulse. Yeah, this is going to be our circuit now, right? Now they are given 4 options, state diagrams, right? Let me write down the option A, right? 1 second. Okay, let us place the variables. Given it is q is equal to 0 1, I think 0 1 0 1 0 1 0 1 0 1 0 1, right? And they are putting a variable, value of a initially, that is a is equal to 1 here. Wait, I have to write it properly. This is a is equal to 1, this is a equal to 0, and they said this is a is equal to 0, this is at a equal to 1. This transition will occur. Similarly, second case they told this is a is equal to 0, right? And this is a is equal to 0, this is a is equal to 1, and this is a is equal to 1, right? And no, this is 0. They said this is 0, right? In option C they told this is a is equal to 0, this is a is equal to 0, this is a is equal to 1, and this is a is equal to 1, this state. Last they told a is equal to 1, and this is a is equal to 1, this is a is equal to 0, a is equal to 0, this is also a equal to 0. Now just we need to draw the state diagram for the given, right? See, that is very simple, and I hope you all remember the state diagram procedure, right? I already told you, right, while discussing about the flip-flop itself, we saw the procedures to develop the state diagram. Of course, it's quite interesting only. Let's see, first of all, given it is a 2 cross 1 mux, we need to understand the output of the mux, right? Now, what is the output of the mux? When A is equal to 0, the mux output will become, see there, when A is approaching 0, the output of the mux will become what? It follows the value of x0. X0 is what? Right? In X0, Q bar is entering. It means output will become Q bar. When A is equal to 1, then output, right, will become what? When A is equal to 1, see there, this is I0. Guys, listen, I hope you all remember, when I was discussing about the multiplexer, I told you, it does not matter at which point your initial pin will be fixed. First I0 will be triggered, and then I1, and then I2, that is, and then I3. That is the order. You will have to trigger X0 first, and then X1, and then X2, X3. That is the order. When A is going to be 0, X0 will be triggered. When A is equal to 1, X1 will be triggered. Clear? Such that when A is approaching 1, automatically what will happen? It follows the value of Q, right? So the output will become Q here. Right? Now, what will be the conclusion here? I understood. Guys, listen. From this, we can just simply make this statement. The statement is, see there, A is equal to 1 means Y is equal to Q. Q means what? Previously என்ன ஸ்டேட் இருந்ததோ அதே ஸ்டேட் திரும்ப வருதுன்னு அர்த்தம். Are you getting me? Right? So output. So இன்னும் உங்களுக்கு தெளிவா புரியணும் அப்படின்னா, actually there will be one more name for your output, that is called QN plus 1. Correcta? Output of the circuit can also be considered as QN plus 1. If you observe like this, now you will get the clear idea. Let us see. Let us consider two states, 0 and 1. Let us consider two states. Now see there, when A approaches 1, next state and present state both are same. See there, Qn plus 1 is equal to Q. It means what? Previous state 0 means present state also 0. Previous state 1 means present state also 1. When A approaches 1, very simple question na. So when A approaches 1, present state is 0, right? Previous state is 0, present state also. Qn plus 1, Qn both are equal. When A is equal to 1, Qn plus 1, that is when A approaches 1, previous state and present state are same. If previous is 1, present also 1. If previous is 0, present also 0. there are two cases. Second case is when A approaches 0, present state will be the complement of the previous state. It means what? If present state is 0, then complement of the present state is 1. Do you all agree with me? This could be possible when A approaches 0. Again, suppose if present state is 1, then its complement is 0 when A approaches 0. There are two cases. If present state is 0, then its complement will become 1. Suppose if present state is 1, then its complement will become 0 when A approaches 0. Clear? So only two observations. That's all. So this is the state diagram. Shall I observe the options? Where is the option? Option D. That's all. See how simply your questions are. But I told you, right? Brain, you'll have to let your brain to work, right? Some practice should be required. That's all. Just you'll have to learn how to play with these circuits, right? Yeah. Let us take the next question. The question is a cascaded 3 identical modulo. The question is a cascaded of 3 identical modulo 5 counters has an overall modulus of right, has an overall modulus of. They said in option A given as 5, in option B which is given as 25, in option C they said 125, in option D they said 625, right? This is 625. Okay guys, listen. In order to count the mod, right, this is very simple. Listen guys, for an example, there are two modulus counter is given. First one is acting as a mod m counter, and with this we are cascading one more counter, and it will act as a mod n counter. It will act as a mod n counter, such that what will be the net mod, right? So the overall mod is, first thing is, let us consider some input frequency also, right? Now here we are going to observe two things, right? First thing, we are going to observe the output frequency, and we are also going to observe the total mod. For an example, for the 3 modulus 5 counter with let me insert one more. Let us improve the question with the input frequency of, right? Let us consider with the input frequency of 125 kilohertz, with input frequency of 125 kilohertz, has an overall modulus of this, let us consider, was an overall modulus under output frequency of, let us consider output frequency of. There are two questions, right? Input frequency is given, modulo is given. Question is output frequency as well as overall modulus. There are two questions. It's very simple. This overall circuit can be redrawn as, right? So the first thing is, let me club them together such that the overall mod is going to be the product of these two, that is m dot n, under the overall output frequency. This is input frequency, whereas output frequency of the circuit is going to be input frequency divided by net modulus of the counter, net mod, such that let us estimate the answer, right? For our case, instead of considering 2 mod, they are considering 3 mods. 3 mods in the sense we have to put them into what? 3 modulus, 3 people will be there. It means 5 cross 5 cross 5. It is going to be the net mod. 3 modulus counters are there. See that they said 3. So 5 cross 5 cross 5. Totally what? 125. So the net mod is what? 125. What about the output frequency? Output frequency, which will be equal to input frequency divided by total mod, is 125. What about the input frequency? They said that is 125 kilohertz. Input frequency is 125 kilohertz divided by mod, such that what will be your answer? It will be equal to 1 kilohertz, right? Output frequency is going to be 1 kilohertz, and the overall mod is, it is the product of, that is cascaded means you'll have to multiply them. That's all, right? Just to remember, this is the relation between cascaded modulus counters and output frequency input frequency relations, right? Fine. Okay, same type of questions, right? Again and again, it is being repeated. Okay, that is very easy given. At sometimes you'll be tested, some other questions will be there. Present state will be given and you are requested to find out the next state and third state, fifth state, like that. We saw how to find out the mod of the counter, like mod 5, mod 6, mod 7 at all. அதே மாதிரி என்ன கேட்பாங்கன்னா, some circuit will be given to you and you are requested to find out the next state, or after 3 clock pulse what will be the state of the circuit, right? So let me take one example for that. We shall take some one example, right? So let me take that one also. Wait a minute. Okay, it's over. Now for an example, let me consider some circuit, right? Some counter is given to you and let me consider 1, 2, 3 blocks, right? And let me take these outputs, let me connect them with the XOR gate. Okay, let me consider XNOR also, no issues. So let me join them together and this is the clock, this is clock. Initial state is given as 1001, right? That is the given circuit. Now the question is, right, find out after the third clock pulse, after the application of third clock pulse, after third clock pulse, what will be the state of the circuit? State of the circuit is what? After the application of third clock pulse, what is the state of the circuit, right? Let us see clock. Let me consider the clock first and then let us consider the initial states. Let me give some name for them: Q0, Q1, Q2, Q3. Just let us consider Q0, Q1, Q2, Q3, right? Initially, without applying clock pulse, already available bits are 1001. Now while applying the first clock, let us see, before, prior to the application of clock pulse, first you have to understand, see that this 0 will come here, this 1 will come here, such that given it is what? XNOR gate. For XNOR gate, we know the inputs A, B, let us consider the output 0, 0, 0, 1, 1, 0, 1, 1. For 0, 0, you will have 1, 0. This is the logic or truth table of the XNOR gate. If I will give 0, 1, output will become 0. If I will give 0, 1, output will become 0, such that 0 will be registered when we are giving the first clock pulse. Automatically what will happen? While giving the first clock pulse, this 1 will be replaced. I think there will be shifting, right? That is shifting. That is your data will be shifted here. Automatically what will happen? The thing is 0 will be injected into the circuit. 0 will come here. This 1 will go here. This 0 will go here. This 0 will go here. Such that it will become 0, 1, 0, 0 while applying the first clock pulse. That's all. It will be shifted, right? Now let us apply the second clock pulse. Now the new data are what? 0, 1, 0, 0. This is 0. This will become 1 under this in 0, 0. Now see there, we are applying 0, 0. If you apply 0, 0, see there, XOR logic, right? So for XNOR, 0, 0, application will produce 1. Now while applying the second clock pulse, 1 will be injected such that here it will be 1. This 0 will go here. This 1 will come here. This 0 will come here. Right? Again, the new data is 1, 0, 1, 0. Again, 1, 0 is going as the input of XNOR logic. Right? Again, output will become, for 1, 0, output will be 0. 0 is waiting to inject, right? Again, while applying the third clock pulse, what will happen? 0 will be injected such that 0 will come here, this 1 will go here, this 0 will come here, this 1 will come here. Now, what is the question? After the third clock pulse, what is the state of the circuit? 0, 1, 0, 1. Clear? That is the answer. You'll be tested for this type of questions, right? The 1 mark or 2 mark, right? In TRB et al, you'll be tested for 2 more question, right? Oh, someone posted your answer for modulus counter. Yeah, feeling happy. Okay, that's all. Sequential circuit is completely over, right? So there is one more important chapter is there in digital. That is, we have to touch that one. Counters, right? Sorry, converters, right? Analog to digital converter, digital to analog converter, right? So tomorrow we will start that one, right? With this, almost we are in the edge of the digital circuit, right? Apart from that, we should touch slightly the basics of the logic families, right? We will see that things, right? Okay, with this your digital is over almost, right? If you have any doubts in our today class, you can post it in our group, right? So let's wind up the class. Thank you all.